Hello everyone. So in today's video, we will be discussing Gauss-Seidel method. So Gauss-Seidel method is just one of the many ways of solving for the roots of our linear system. So Gauss-Seidel method is under the iterative methods for solving linear systems because we will be having iterative repetitive process of solving our system in order for us to get the closer approximation or the closer result of our roots of our linear system. So basically, for example, if we have this linear systems or linear equations here, we have a sub 11 x sub 1 plus a sub 12 x sub 2 plus a sub 13 x sub 3 is equivalent to b sub 1. So for this systems here, we need to isolate the x sub 1, x sub 2, and x sub 3. So again, from the first equation, we can isolate the x sub 1. So by isolating this one, we'll need to move all the other equations or all the other variables to the other side of our equation, which gives us b sub 1 minus a sub 12 x sub 12 minus a sub 13 x sub 3, and then we need to divide that by the coefficient of our x sub 1 in order for us to isolate the value of our x sub 1. So repeating the process, we also need to find the equation of our x sub 2 here from the second equation or from the second linear system. So we can have b sub 2 minus this one minus this and divided by the coefficient of our x sub 2, which is a 22 or a sub 22. And then the same process, we need to find again the equation of our x sub 3. And repeating the same process, we just need to move the other equations or other variables to the other side of our equation. So that gives us x sub 1, x sub 2, and x sub 3. Now we already got the equations of our x sub 1, x sub 2, and x sub 3. Then we can already use that one for the um, later solving for the roots of our linear systems. Now, as you can see, class, you need to remember that the values or the coefficients of the diagonal the diagonal values here must have the bigger coefficient value than the other um, variables that we have here, than the other terms that we have. Meaning to say, a11, the value of our a sub 11 must have the bigger value than the sum of this one, of the two. So meaning to say, if this is 12, the other coefficients must be less than 12 so that we can retain the same process or the same position that it has. So for the similarly, a22 coefficient of a22 must have the bigger coefficient value than the other coefficients it has in its linear system. Same goes as the value of our a sub 33. A sub 33 must have the bigger value or must have the bigger coefficient than the other coefficients of its linear system. But however, if the coefficient given that it is not on a diagonal dominance, meaning to say you need to rearrange the system in order for us to get the diagonal dominance. Meaning to say, in the diagonal dominance, the coefficients within the diagonal dominance must have the bigger value than the other terms in the linear system. So if A12 has the bigger value than A11, you need to rearrange our equation in order for us to get A12 or A sub 12 in this position. But in any case that the diagonal dominance has already the biggest value than the other terms, that is already good for solving for the roots of our equations. So you need to remember that one, that again, if the diagonal dominance must have the biggest coefficient value than the other coefficients it has in the linear system. So before we move on to to an example, I just have to discuss first what is the content of the ULO or the content of your sim. So from here, you can see we have here the example. For the linear equations below, find the unknowns using Gauss-Seidel with e raised to k is equivalent to x raised to k plus 1 minus x raised to k is less than 0.001. So e raised to k here is the relative error or the accepted relative error for the equation. So meaning to say the relative error must be less than 0.001. So in this case, as an example, we have here in the table that we have, the relative error must be again less than 0.001. So as you can see, the relative error of our first iteration or iterative one is still greater than 0.001. So since it is still greater, you need to repeat the same process again and then check again if the error is still greater than 0.001, then you need to do the another step or the same process again until such time that the relative error is already less than 0.001. So if it's already less than 0.001, that is already the accepted relative error of our equation. So as you can see here, 0.00058 and the same as the others are less than already with 0.001. So meaning to say, the roots that we have here is already the approximated roots to solve our linear system. So this is how we solve our Gauss-Seidel method, our problems using Gauss-Seidel method. So we have here an example. Use the Gauss-Seidel method to solve the following system until the percent relative error falls below 5%. So 5%, that is also equivalent to 0.05. Right? So meaning to say our relative error or our EK must be less than 0.05. So from the system or from the linear systems that we have here, as you can see, the diagonal dominant and the diagonal coefficients are already dominant. So meaning to say we can already start isolating for the equation of our x sub 1, x sub 2, and our x sub 3. So that being said, we know x sub 1 is equivalent to this one. We have 27 minus 2x sub 2 plus x sub 3 all over the coefficient of our x sub 1, which is 10. So this is now the equation of our x sub 1. For x sub 2, we have equivalent to negative 61.5 plus 3x sub 1 minus our 2x sub 3 all over the coefficient of our x sub 2, which is negative 6, which is also equivalent to positive 61.5 minus 3x sub 1 plus 2x sub 3 divided by positive 6. So basically that's just equivalent, right? Because negative divided by negative is positive, positive divided by negative is negative, negative divided by negative is positive. So that's just equal with each other. So we have x sub 3 is equivalent to negative 21.5 minus our x sub 1 minus our x sub 2 all over the coefficient of our x sub 3, which is 5. So meaning to say this is already our equation for x sub 1, equation for x sub 2, and equation for x sub 3. So that being said, it is easier to rewrite our equations in a table form so that we can easily track the changes between the iterations that we will be having. So we have the x sub 1, we have the x sub 2, we have the x sub 3. We also have the relative error in terms of x sub 1, which is equivalent to the absolute value of our x raised to k plus 1 minus x raised to k, and the absolute and the error or a relative error of our x sub 2, that is equivalent to the absolute value of the same equation. We have x k plus 1 minus our x raised to k, and the same as the relative error of our x sub 3, which is equivalent to the absolute value of our x k plus 1 minus our x raised to k. So this is the needed details or the needed values for our to solve our Gauss-Seidel method. So now let's start with the iteration or initial iteration, which is the 0, meaning to say we can also initialize our x sub 1, x sub 2, and x sub 3 is equivalent to 0. So for that one, we have our initial iteration as, or k is equal to 0, and we have the values of our x sub 1, x sub 2, and x sub 3 is equal to 0. So for the first iteration now, we will be using the equations that we have here. 27, for the x sub 1, we have 27 minus 2, x sub 2 plus x sub 3. And we know that x sub 2 and x sub 3 is equivalent to 0. So you just have to substitute that one here in our equation. So we have 27 minus 2 times 0 plus 0 divided by 10. That is equivalent to 2.7 if you substitute that here. And then afterwards, for the x sub 2, we will be using this equation here. We will be using this equation for x sub 1, x sub 2, and this one for the x sub 3. So for the x sub 2, since we already got the value of our x sub 1, then that will be the value that we'll be substituting here. So we have 61 minus 5, 61 minus 0.5 minus 3 times 2.7 plus 2. Since we don't have any values yet for our x sub 3, then we have the 0. We need to substitute that by 0. And then divide it by 6. Then that is equivalent to 8.9. So you have to put that here, 8.9. So the same process, we need to substitute for the x sub 3, we need to substitute x sub 1 and x sub 2 since we already got the values of our x sub 1 and x sub 2. Then we need to substitute that there. So negative 21.5 minus 2.7 minus 8.9 divided by 5, that is negative 6.62. So afterwards, in getting the relative error of our x sub 1, x sub 2, and x sub 3, you just have to subtract the x raised to k plus 1 minus x raised to k. What do you mean by x raised to k plus 1? Meaning to say, our initial value or our k earlier was 0, right? Mean this one. So meaning to say, you just have to subtract the value of our x sub 1 by the value of its previous value. So meaning to say, uh, so meaning to say 2.7 minus 0, that is still 2.7. 8.9 minus 0, that is 8.9. And 6.62 minus 0, that is still 6.62. Again, that is absolute value, so there's no need to copy the sign. So we already have this relative error. Again, the objective of our relative error must be less than 0.05. Right? So since as you can see, this is not yet less than 0.05, then we'll need to continue with another iteration. So that gives us this one. So using the same process again, substituting the values that we have, 27 minus 2, x sub 2. In this case, our x sub 2 is 8.9 plus our x sub 3, which is negative 6.62 all over 10. So that gives us 0.258. Now class, you need to understand that you need to get 6 decimal points here if possible. You need to use 6 decimal points. But since this one, if you calculate this one, that is just equivalent to 0.258. So just copy 0.258. And then afterwards, the same process, you need to do the x sub 2 now. 61.5 minus 3 times 0.258 plus 2x x of 3, which is negative 6.62 all over 6, that is equivalent to 7.914333. So if you calculate that one, class, I just pre-calculated it earlier, so you just have to calculate that with yourself to check also. So we have here. And then we have the x of 3, which is negative 21.5 minus x of 1, which is this one. Again, you need to use the much later value that we have for the roots of our system. So we have 0.258 minus 7.914333 all over 5. So that gives us negative 5.93447. Again, 6 decimal points. You need to write 6 decimal points. And again, you need to be careful because once you got the wrong answer, or once you write the wrong answer from the first or the first step or the previous step, that will lead to a um, a incorrect answer at the later part. So you just have to really be careful with this one, because this is a lot if you will recheck this one after. So again, to check the relative error, 0.258 minus 2.7, that is equivalent to negative, but we need to use the absolute value, so that gives us 2.442, which is still not acceptable because of this one. And then for the x of 2, we have 0.985667. And for the EK, this one minus this is equivalent to 0.685533. And then, as you can see, this is not yet acceptable, so we need to have another iteration again. So that gives us our third iteration. So using the same process repetitively, we have here 0.523687. And for this one, for the x of 2, again, 61.5 minus 3 multiplied by the recent value of our x of 1 plus 2, and the latest value of our x of 3, which is negative 5.934467 divided by 6. That gives us 8.010000. Since this one is already 000, you can just opt to not write that one. You can just write 8.01. And for the x of 3, we have substituting the values here. We have negative 6.00637. And then checking the relative error, we have 0.265687. And for the other one, we have 0.095667. Then for the XL3, we have 0.07227. So as you can see, it is almost there. We are almost below 0.05, as you can see here. Then we can have another iteration again. So substituting the values again, we have 0.497326. And then for this one, we have 7.97880. Then we have negative 5.995241. Then checking the relative error, Subtracting this row from this row, we have 0.026361. And then we have 0.03112. And for the last one, we have 0.0115. So as you can see, this one, our relative error is already less than 0.05. All of our relative errors are already less than 0.05. So meaning to say, we have our roots of our equation, which is x sub 1 is equivalent to 0.497326. We have x sub 2 is equivalent to 7.9788880, and x sub 3 that is equivalent to negative 5.995241. Now checking this one, rechecking this one, if we have the correct value, checking that this one if we have the correct roots of our equation, we can substitute that to our given linear equation. So if you substitute that one, and it will give us this answer. If you substitute to the left side of our equation and gives us to the equivalent to the right side, or approximately equivalent to the right side, then that is already the correct answer. So let's try to substitute this one. We have 10. Just have to rewrite it here. We have 10 multiplied by x sub 1, which is 0.497326, plus 2 multiplied by 7.9788880. And then we have our minus x sub 3, which is negative 5.995241. Now, if you calculate this one, this is approximately equivalent. This must be approximately equivalent to 27. So the same process, if you substitute the values here, that should be approximately equivalent to 61.5 and negative 21.5. So if you can see that is already closer, or it is really approximately equivalent to our 61.5 or 21.5, then that is already the correct answer. So those were all the discussion for the Gauss-Seidel method. I hope you learned something. I hope your confusions are already answered in this video. But if you still have any confusions, you can message me in our LMS or in our group chat in our messenger. So thank you and have a great day.